You are on a late afternoon street lined with pre-1920 commercial blocks, cast iron storefronts below and heavy masonry above when you do what nobody does anymore. You look up. On the roofline of a 1905 downtown bank building, the kind with a carved cornice and a corner cupola, you spot a thin metal tower that does not match the architecture. You have been told it is just decoration or just a lightning rod, but the rod is not a single spike. It is a cluster tied into ceramic standoff insulators bolted to the parapet, hardware you do not buy for looks. The quick explanation breaks immediately. A lightning rod wants the shortest, fattest path to ground. So why do you see multiple conductors, insulated separation, and symmetrical routing like a planned circuit? Here is the contradiction. If it is ornamental, why is it built like infrastructure? And if it is infrastructure, why did the story get simplified? I promise you can trace this, photograph it, and match it to period language. No guesswork required. Walk closer to that 1890s bank building on the corner of Main and Court. Typical county seat core, 5 stories of load-bearing brick with limestone trim. The parapet-mounted framework you noticed is not alone. Count the terminals, 4 vertical copper rods, each about 8 feet tall, spaced evenly along the roofline. At the base of each rod you will see ceramic insulators, white porcelain standoffs weathered but intact, bolting the assembly to the parapet cap with visible bronze hardware. The weathering pattern matters. This is not a recent addition. The patina matches the building's original downspouts and window lintels. Lightning protection in the 1890s followed specific logic documented in every building trades manual. A single air terminal at the highest point connected to a thick copper conductor running straight down to ground. What you are seeing contradicts that in 3 ways. First, multiple terminals instead of one spike. Second, ceramic insulation separating each conductor from the masonry, deliberate electrical isolation where a lightning rod would want contact. Third, the conductors do not run straight down. They angle inward toward the roofline edge, then disappear through small penetrations ringed by ceramic bushings, purpose-made components from electrical supply catalogs. The terminals are not clustered randomly. They are symmetrically distributed with even spacing and clear sight lines to the sky. That is not decorative balance, that is systematic exposure geometry. You can still photograph the bolt pattern and insulator spacing from the sidewalk. Compare it to a true lightning rod on the adjacent courthouse. Single spike, direct run, heavy gauge conductor, visible to ground. The bank's hardware is lighter, more distributed, deliberately isolated. The first clue is simple. This is wired like a system, not posed like an ornament. 3 blocks north, a 1908 hotel rises 6 stories with a decorative cornice. The roofline shows a low metal framework along the parapet's inner edge, almost hidden unless you are directly below. Mounted to that framework are porcelain standoffs, each about 4 inches tall and spaced at regular intervals. These are not decorative finials, they are functional hardware, identical to insulators used in telegraph lines and early power distribution. Check the 1897 Thomas & Betts catalogue, which lists porcelain knobs and feed-through insulators in standardized sizes matching what you are seeing. The conductor threading through these insulators is copper wire, about 1/8 of an inch in diameter, oxidized to a brown-green color. It runs horizontally along the parapet, connecting each insulator in series, and then angles down toward the building interior at 2 points. The separation from masonry is consistent, about 3 inches of air gap maintained by the insulator height. This is engineered clearance, specified in installation manuals to prevent leakage paths. Why insulate here? In decorative installations, there is no reason to isolate metal from the building. In standard lightning protection, you would want the opposite, solid bonding to masonry. But if the system collects and routes electrical charge without letting it dissipate prematurely, insulation makes sense. You are seeing evidence of intentional control, conductors kept electrically separate except at specific entry points. Compare these insulators to the uninsulated brackets holding the hotel's rain gutters. The difference is immediate. The roof conductors are isolated, utilitarian metalwork is not. That distinction matters. Insulation is step one in managing charge flow, so where does it go next? In a converted 1912 textile loft, you can trace the interior side if you access the top floor service corridor. The roof hatch frame shows two ceramic bushings, painted over but recognizable by their glossy texture. These are entry points for conductors from the roof array. In the adjacent stair core, patched penetrations mark where something passed through the wall, rectangular cutouts filled with lighter mortar. In the basement, near the electrical service entrance, wooden backboards show ghost brackets, faint outlines where metal clamps once held equipment. The geometry matters. Roof entry points, stair core penetrations, and basement backboard locations form a vertical path. Collection points on the roof, protected routing through the service spine. Termination hardware in the basement. This is distribution logic, the same spatial planning you would see in early telephone systems or direct current power networks. One detail stands out. A rectangular paint shadow on the backboard, about 18 inches wide and 30 inches tall, is darker than the surrounding wood. Something mounted there for years protected the wood from grime. Measure the shadow perimeter. There are 4 sets of mounting holes in a symmetrical pattern. The bolt spacing is approximately 12 inches horizontally and 24 inches vertically, consistent with early electrical cabinet footprints. But there is a mismatch. Standard panels had 1 or 2 main inputs from street power. The basement backboard shows evidence of multiple inputs from above, at least 3 separate conductor entries, each through its own ceramic bushing. That is not how grid-supplied panels were wired. It is consistent with collecting inputs from distributed rooftop sources and consolidating them for regulation. If there was a cabinet, what was it doing? Storage, regulation, or switching? The hardware is not unique to one city. Banks built between 1885 and 1915 share a common rooftop profile across different architectural styles. The same insulator families appear. White porcelain standoffs and brown ceramic knobs. The same bracket geometry appears, L-shaped iron brackets bolted to parapet caps. The same symmetrical layouts appear, terminals distributed evenly and often mirrored left to right. Consider the 1890 First National Bank in Ohio with 4 terminals parapet mounted and ceramic insulated. Compare it to the 1903 Guarantee Trust in New York. Also 4 terminals with the same mounting method and the same spacing. Neither building is architecturally notable, yet both have nearly identical rooftop installations, suggesting standardized procurement rather than custom design. This repetition implies a market. In the 1897 Electrical Supply Company catalog, line drawings show roof terminals and atmospheric apparatus hardware, not lightning rods which appear in a separate section, and they include part numbers and pricing. A 4-inch porcelain standoff cost 12 cents. An L bracket cost 35 cents. A collector terminal assembly cost $2.50. These were catalog goods, not bespoke items. Procurement language reveals purpose. The Minneapolis City Hall specifications from 1891 include both a standard lightning rod system meeting National Board requirements and atmospheric terminals with an interior regulation cabinet listed as the contractor's choice of an approved system. 2 separate installations, 2 different purposes, distinct contract language. Make a photo grid of civic and commercial buildings built before 1915. Focus on corners and parapet midpoints. You will see the same standoff spacing, typically 10 to 15 feet between terminals. You will see the same conductor routing, horizontal runs, then inward turns toward penetrations. You will see the same weathering, copper oxidation, ceramic crazing, and iron rust, all indicating original era installations. What system requires roof exposure, isolation, and interior routing across premium building types? Repetition is the evidence, and it points to a market, who sold it and what did they call it. A 1900s municipal building with an octagonal cupola hosts a standard lightning rod at the flagpole peak, grounded via a thick copper strap. But there is also a secondary array lower on the tower parapet, 6 smaller terminals arranged hexagonally around the perimeter, connected by a horizontal ring conductor and insulated from the tower by ceramic standoffs. The ring feeds into a single lead-in cable descending through the interior stairwell. This secondary array is not trying to intercept lightning strikes. That is the tall rod's job. These terminals are positioned for distributed collection across the tower perimeter. Each has clear sky exposure with minimal shadowing. The hexagonal spacing creates overlapping collection zones regardless of weather approach direction. This geometry matches Patent US 465,318, filed in 1891, which describes an improved system for the collection of atmospheric electricity comprising a plurality of elevated terminals arranged in a substantially circular or polygonal pattern, connected by a common conductor to a storage or regulation apparatus. The patent explicitly describes the system as supplemental and suitable for charging storage batteries or operating low-current instruments. What applications make sense for intermittent, low-power sources? In the 1890s and the 1900s, telegraph relay systems needing only milliamps, burglar alarm panels requiring periodic battery recharging, slowly operating electroplating equipment, and demonstration apparatus for science education. The tower array shows careful air gaps. The ring conductor maintains a 3-inch separation from parapet masonry. Each terminal passes through a ceramic bushing before connecting to the ring. No accidental contact is possible. This is isolation work consistent with managing high impedance, low current flows where leakage to ground would drain collected charge. If the system collects anything, it needs a regulator, a place where intermittent inputs are stabilized or stored. Follow the lead-in cable down through the stairwell to the basement mechanical room, where a rectangular outline on the foundation wall tells the next part of the story. In a 1910s office block mechanical room, the walls show a rectangular paint shadow about 16 inches by 28 inches with 4 threaded mounting holes. 3 ceramic feed-through bushings are set into the brick at waist height in a triangular pattern, currently empty but clean inside. Measure the bolt spacing, 12 inches horizontal and 24 inches vertical. Standard residential panels were 10 by 14 inches. Industrial switchgear was 3 feet or more. This size falls between those, large enough for multiple components but not industrial scale. Equipment catalogs show storage battery charging panels and auxiliary regulation cabinets in this range. The 1908 Western Electric catalog includes a battery charging and regulation panel at 18 by 30 inches, featuring a voltmeter, an ammeter, a disconnect switch, and a series parallel selector almost exactly the shadow size. 3 feed-through bushings suggest 3 incoming conductors, more than expected for a battery charger fed from building power. But if inputs came from rooftop collection points, 3 conductors make sense. The triangular arrangement would prevent phase confusion and allow balanced monitoring. A cabinet here fed by 3 rooftop conductors would serve as consolidation and regulation. Atmospheric collection systems in period literature consistently emphasize voltage regulation and storage. Collected potential varied with weather conditions. Direct connection to loads would be impractical. Instead, the system would charge a battery bank, supplying a stable voltage to low-demand applications. The absence of heavy bus bars matters. Standard building power used 1/4-inch or larger conductors. The bushings here have bore holes for 1/8-inch conductors. That is consistent with low current operation, enough for instrumentation, signaling, or trickle charging, but not for significant loads. An 1/8-inch copper conductor safely carries about 10 amperes at low voltage. 4 terminals in parallel could provide up to 40 amperes, enough for a few lamps or signal circuits. This is supplemental capacity, not replacement power. A hotel from 1905 with electric lobby lighting and call bells helps define realistic expectations. The rooftop array is modest, 4 terminals on the main building. Conductors are thin, 1/8-inch diameter. Interior routing uses small conduit, not heavy raceways. The basement cabinet shadow suggests a panel no larger than modern breaker boxes. Overall capacity, 4 terminals at 10 amperes each, yields 40 amperes maximum, enough for 4 or 5 incandescent lamps or for signal circuits. Not free city power, but supplemental capacity for targeted uses. The magazine Electrical World in 1893 described experimental installations on commercial buildings, noting collected potentials varied from a few volts during calm weather to hundreds during storms. Practical applications required storage batteries to smooth the supply and prevent damage. The article said atmospheric collection was suitable for charging alarm circuits, operating telegraph instruments, and demonstrating electrical phenomena, but not reliable enough for general illumination. That matches the physical evidence. Small conductors, modest cabinet footprint, and limited routing all point towards situational use. The system was not designed to power an entire hotel, but to supplement specific low-power circuits, possibly reducing battery replacement costs for alarms or serving as demonstration features. Another constraint was maintenance. Rooftop arrays exposed to weather required periodic inspection and cleaning. Insulators accumulated dirt, reducing effectiveness. Copper oxidized, increasing resistance. Connections corroded. In buildings before 1920, without easy roof access, this work was labor-intensive overhead. The trade press supports this interpretation. The American architect in 1901 described installations in New Jersey and Massachusetts, noting they successfully demonstrated feasibility of collecting atmospheric potential, but proved less economical than anticipated because of variability of yield and ongoing maintenance requirements. The article treated it as legitimate but ultimately impractical. The hotel's array traces that trajectory. It was real enough to install, functional enough to use, and marginal enough to abandon when better alternatives became standard. If it was real enough to install widely, there should be a paper trail with the right words. Start with terminology. In archived electrical catalogues from the period, this hardware appears under specific headings. The 1897 Thomas and Betts catalogue lists atmospheric electrical apparatus separate from lightning protection equipment, including collector terminals, insulated lead-in fittings, regulation panels, and storage battery connections. Each entry has part numbers, dimensions, and pricing, standardized commercial product. Patents use similar language. Search the US Patent Office database for atmospheric electricity, collector, aerial conductor, and electrical storage. You will find dozens describing rooftop collection arrays, insulated routing, and consolidation cabinets. Many explicitly claim improvements in systems for collecting atmospheric electrical potential for storage and use in low-current applications. The inventors are not vague. They describe functional devices for practical installation. Municipal permits provide verification. Building permits from the 1890s and the early 1900s sometimes listed atmospheric apparatus installation distinct from general electrical wiring and lightning rod installation. Cleveland's 1896 building department records show permits for atmospheric collection system with storage regulation on 3 downtown buildings, a bank, a hotel, and a municipal office. The permits include contractor names, costs, and inspection dates, bureaucratic paperwork treating these as legitimate infrastructure. Match photographed hardware to catalogue drawings. The insulators on that 1905 bank compare to the 4-inch porcelain standoff Type B on page 47 of the 1899 Electrical Supply Catalogue. The L brackets match page 52, parapet mounting hardware standard pattern. The ceramic bushings match page 61 wall penetration insulators. The drawings match, same profile, same geometry, same dimensions. Purpose-designed parts were sold specifically for rooftop electrical collection. Contract specifications add detail. An 1893 Pennsylvania courthouse specification required the contractor to provide and install atmospheric collection terminals on the tower roof, with insulated conductors led to a storage cabinet in the basement electrical room per approved practice. Direct, unambiguous language describes a system modern surveys simplify to decorative metalwork. The terminology hunt matters because words locate vendors, and vendors locate standard installations. The paper trail confirms this existed as documented practice. Any system involving rooftop installations, interior wiring, and electrical cabinets triggered building code oversight. The 1902 National Electrical Code included a section on auxiliary electrical apparatus describing installations beyond standard building power. Code oversight treated these as part of the built electrical infrastructure. The section specified that conductors for atmospheric collection systems shall be isolated from building structure by approved insulators, and that storage or regulation cabinets shall be installed in dry, accessible locations with adequate ventilation. These are mandatory requirements for inspected installations. Building inspection records confirm compliance. A 1907 Chicago office building inspection report notes that the rooftop collection array was inspected, that conductors were properly insulated, that lead-in bushings were installed per code, and that the storage cabinet was accessible and properly grounded. Inspector signature, date, and address were documented, treating the system as routine infrastructure. Fire underwriter rules add further documentation. Insurance companies required electrical installations be inspected before policies were issued. Requirements for atmospheric electrical systems appear in period underwriter manuals, specifying minimum conductor sizes, required insulator types, acceptable cabinet locations, and separation distances from combustibles. What is revealing is how requirements change over time. Early manuals from the 1890s treat atmospheric collection as an emerging technology requiring careful specification. By the 1910s, references become briefer and standardized, suggesting installations had become routine. By the 1920s, references largely disappear. That timeline matches physical evidence, with installations common from the 1890s through the 1910s, and decommissioning beginning in the 1920s as municipal grid power became reliable. The documentation also shows these systems were never universal. Code sections note installations were optional auxiliary equipment rather than required systems. Insurance rules treated them as specialty installations requiring additional inspection but not standard protection like lightning rods. The documentation confirms this was a niche market serving specific clients, not a widespread practice. Check city archives and underwriter manuals for permit categories and inspection language. If systems were installed, permits were issued, inspections were conducted, and insurance policies were written with specific equipment clauses. The bureaucracy documents what was actually built, inspected, and insured using period terminology. If atmospheric apparatus triggered permits, inspections, and insurance requirements, then documentation exists. If codes mention systems early and then the vocabulary disappears, that is evidence of technological obsolescence and simple replacement by superior alternatives. Archival photographs provide visual proof. In skyline shots from the 1890s and the 1900s, rooftop arrays are visible as deliberate installations. A 1904 Denver photograph from the Capitol Dome shows at least 5 buildings with rooftop terminal arrays, multiple vertical elements with horizontal connecting runs. The arrays are not hidden, they are part of the building's visible profile, documented alongside smokestacks, elevator penthouses, and flagpoles. Museum collections preserve physical examples. The Smithsonian Electricity Collection includes atmospheric collection apparatus circa from 1895 to 1910, a regulation cabinet with voltmeter, ammeter, knife switch, and connection terminals. The interior shows actual use, with tarnished contacts, oxidized copper bus bars, and period labels indicating voltage ratings. Worn equipment that spent years in service. Engineering details show installation specifics. The Library of Congress holds several patent drawings and contractor plans. One 1896 set shows a Cleveland Bank rooftop array with terminal placement, conductor routing, insulator specifications, and cabinet location drawn to scale with dimension annotations. A parts list includes catalog numbers referencing specific supplier inventory, working documents that guided actual construction. Construction photographs reveal timing. A 1902 Buffalo hotel under construction shows workers mounting terminal assemblies while other crews finish interior plaster. The terminals are installed during systems commissioning, not added as decorative touches after completion. That is infrastructure timing. Maintenance photographs provide operational evidence. A 1910 Philadelphia office building maintenance album includes rooftop array inspection images showing insulator condition, conductor connections, and terminal weathering. Annotations discuss cleaning required and conductor replacement recommended. This is inspection-level detail. The language used is operational, a maintenance language for functional equipment. These were not ornamental details, they were part of the building operational systems. Compare construction photos to later images. In many cases, arrays visible in photographs taken before 1920 are absent in photographs taken after 1930. Removals occurred during documented renovation periods when buildings were upgraded for new electrical standards. These removals are often recorded in permits and reports. Arrays are not preserved because they are no longer functional. Mounting hardware sometimes remains. Orphaned brackets and unused insulators remain, ghost evidence of removed systems. These orphaned parts point to former installations. The evidence exists in photographs, museum collections, and engineering drawings. Installations were real, documented, and treated as building infrastructure. The question is not whether they existed. The record confirms they did. The question is why modern buildings keep the shells but lose the story. By the 1920s, the economic case collapsed. Municipal grid power was reliable, standardized, and inexpensive. A kilowatt-hour cost pennies with consistent voltage and effectively unlimited capacity. This shift favored the grid. Atmospheric apparatus required maintenance, delivered intermittent output, and could not scale. The choice was obvious: remove the marginal system, salvage valuable materials, and standardize on grid power. That practical decision, driven by maintenance burdens and economics, prompted widespread abandonment. Renovation contracts document decommissioning. A 1924 hotel modernization contract includes removal and salvage of existing atmospheric collection apparatus, including rooftop terminals, interior conductors, and regulation cabinet, and it specifies that copper and brass should be salvaged and credited against project cost. Copper fetched 15 to 20 cents per pound, enough to offset removal labor. The pattern reveals priorities. Interior components, cabinets, conductors, switches, and meters disappeared quickly because they had salvage value and occupied usable space. But rooftop terminals often remained because removal required expensive roof access for minimal return, and weathered metalwork was difficult to detach without disturbing the roof membrane. Labor exceeded salvage value, so rooftop shells stayed. Look for clean cuts versus corrosion breaks. Clean cuts, smooth and perpendicular edges, indicate deliberate removal at accessible points where copper was worth recovering. Corrosion breaks, ragged and oxidized failures, indicate abandonment and decades of weathering. Decommissioned buildings show clean cuts at interior access points and corroded remains at rooftops where removal cost more than value. Patched penetrations mark salvage activity. Where conductors once passed through walls, you will find repair work such as mismatched brick, different mortar colors, and plaster patches. Compare patch mortar to original building mortar. Patches are often lighter, smoother, and lack weathering, which dates the repair to later renovations. The economics are straightforward. An installation might have cost from $150 to $300 in 1900. By 1925, an electrical service upgrade to full grid power cost from $500 to $800. The atmospheric system could not be upgraded, it required complete removal and replacement. copper salvage might recover from $20 to $40. Decommissioning made financial sense. Why did rooftop hardware remain? Simple pragmatism. Once the functional core was gone, with interior conductors cut and the cabinet removed, rooftop remnants became cosmetically harmless. They did not leak, did not cause safety issues, and did not interfere with new systems. Removing them risked roof damage to recover a few dollars of corroded metal. Economically, abandonment made sense. Once the functional core is gone, what happens to the label? Once cabinets were removed and conductors salvaged, what remained became subject to reinterpretation. Building owners and maintenance staff encountered orphaned hardware, insulators, brackets, and weathered terminals without functional context. The natural response was a simple explanation: decorative metalwork or lightning protection. Both seemed plausible and required no investigation. Relabeling was not deliberate falsification. It was gradual simplification driven by knowledge loss. As original contractors retired and practices changed, the expertise needed to recognize atmospheric apparatus faded. Younger electricians trained in the 1930s and the 1940s learned municipal grid power systems and lightning protection, but they had no exposure to atmospheric collection technology. When asked about early 20th century rooftop hardware, they offered familiar explanations such as probably a lightning rod or old decoration. Trade school curricula document this transition. Electrical manuals from the 1890s through the 1910s sometimes included sections on auxiliary power sources and atmospheric collection apparatus. By the 1930s, those sections disappeared, replaced by alternating current distribution, motor controls, and modern switchgear. The vocabulary dropped from training materials. Electricians entering after 1930 had no framework for identifying atmospheric apparatus because training never mentioned it existed. Building surveys accelerated relabeling. When cities conducted architectural inventories in post-war decades, survey teams lacked electrical history expertise. Forms routinely noted decorative metal finials or lightning rod assemblies based on visual appearance without investigating mounting methods or interior traces. These simplified labels entered official records. Compare early descriptions to later surveys. A 1908 hotel permit describes atmospheric collection terminals, 4 units, parapet mounted with insulated lead-ins. A 1965 architectural survey of the same building notes ornamental metal roof finials, 4 units, original installation. The hardware did not change, the interpretation did. The process chain was straightforward. Installations stopped in the 1910s, interior components were removed in the 1920s and the 1930s, rooftop hardware became orphaned, original explanations faded as expertise retired, simplified labels filled the gap, and new manuals codified simplified interpretations. Each step was rational, but the cumulative effect was erasure of a documented building system category. Post-war roof replacement sealed reinterpretation. Work orders noted preserve existing lightning rod mounts or replace decorative metal fixtures as needed. Preserved elements were treated as architectural features rather than system components. Replacement materials no longer matched original installation logic. Physical system coherence was broken, leaving isolated elements lacking obvious connection. Walk any county seat downtown built before 1920 and look at roof lines systematically. Banks, hotels, and municipal buildings. You will see a motif repeating: ceramic insulators at regular intervals and brackets that do not match decorative hardware elsewhere. Individually, each could be dismissed. Collectively, they form a pattern. The pattern has 3 components: rooftop hardware designed for sky exposure and electrical isolation, interior penetration points showing protected routing, and basement traces suggesting regulation equipment. No building shows all 3 intact. Functional cores were removed decades ago, but remnants across buildings triangulate into a coherent system interpretation. Match visible hardware to period catalogues. The 1897 Thomas & Betts catalogue, the 1899 Electrical Supply catalogue, and the 1902 Western Electric catalogue all show atmospheric apparatus components with dimensions and part numbers. Photographed insulators match Type B porcelain standoff. Mounting brackets match parapet hardware in a standard pattern, not approximate, specific down to bolt spacing and profile. Cross-reference with code language. The 1902 National Electrical Code specifies auxiliary electrical apparatus installation requirements that match the physical evidence: insulated conductors, approved insulators, protected routing, and accessible cabinets. Archival photographs back this up. Skyline images from the 1890s through the 1910s show rooftop arrays on multiple buildings. Construction progress photos show arrays installed during electrical commissioning, not added as decoration. The visual record confirms these installations were treated as infrastructure. Layer in patent documentation. Dozens of patents filed from 1885 to 1915 describe atmospheric electrical collection systems with detailed claims about rooftop terminals, insulated routing, battery connections, and regulation circuitry. Patent drawings show geometries matching physical traces. These patents align with what we see on buildings. Consider removal evidence. Renovation contracts from the 1920s and 1930s document removal of atmospheric collection apparatus with salvage credit. Patched penetrations, cut conductors, and cabinet footprints show where components were extracted. Such removal traces are common in basements and mechanical spaces. What does the evidence support? An obsolete, low-power, supplemental electrical practice. Atmospheric collection apparatus on commercial and civic buildings from roughly 1885 to 1915. Systems collected atmospheric potential via rooftop terminals, routed it through insulated conductors to regulation cabinets, stored charge in batteries, and supplied low-current applications. The technology was documented in patents, sold through catalogs, installed by contractors, inspected under codes, and insured by underwriters. This is clear evidence of a built practice. The systems were practical but limited. Intermittent, low-power output made sense for niche applications, but could not scale. Maintenance added ongoing costs. As grid power became reliable and inexpensive in the 1910s and 1920s, the economic case collapsed. Buildings decommissioned systems, salvaging interior components and abandoning rooftop hardware that was not worth the removal cost. The functional category disappeared from curricula, manuals, and surveys. Later generations encountered remnants without context and assigned simplified explanations. Relabeling was not conspiratorial. It was ordinary simplification driven by knowledge loss and absence of ongoing relevance. Keep context in mind when you encounter orphaned hardware. You can walk this verification yourself. Identify a building built before 1920 with rooftop hardware showing ceramic insulators and systematic mounting. Photograph it. Compare to period catalogs, match profiles, count holes, and measure spacing. Check permits and codes from the installation era for mentions of atmospheric apparatus. Access basements or mechanical spaces and look for cabinet footprints, patched penetrations, and conductor entries. Document the traces systematically. The evidence does not prove these systems worked well. Maintenance records and technical assessments make clear they were marginal, even when new, but the evidence proves they existed as documented building practice, designed, sold, installed, inspected, and used for specific applications before replacement by superior alternatives. Obsolete does not mean imaginary, it means a better alternative one. The rooftop towers are still there, ceramic insulators weathering on parapets, mounting brackets holding nothing, penetrations patched and forgotten. Same hardware, different understanding. Not decoration, not delusion, infrastructure that outlasted its function.